Hello students, welcome to the 15th session of 6th class. Myself Latha N, Assistant Professor of Government First Grade College. The learning objectives of this unit were already discussed in the previous sessions. Topics covered in this session are AC circuit containing pure resistance, AC circuit consisting of pure inductance, and AC circuit consisting of pure capacitance, and AC circuit consisting of inductor and resistor. First, we will study about AC circuit consisting of resistance. Consider a circuit which an AC voltage is applied to a resistor. Then the applied voltage is represented as V is equal to V naught sine omega t. We know that current through the circuit will be equal to I is equal to V by R. That I will be the current through the circuit and V is the applied voltage or potential and R is the resistance of a resistor. So, in place of V, we can write V is equal to V naught sine omega t divided by R. Current at any instant of time is given by I is equal to I naught sine omega t. So, if we plot a graph of I and V, so we can observe here I and V are moving with same phase. If we substitute I is equal to I naught sine omega t, sin omega t will be cancelled. Then I naught is equal to V by R. That is the peak value of current. If we plot a graph of current or voltage versus phase, so we can observe current is in the same direction and voltage is also in the same direction. So there is no phase difference between the voltage as well as current. So therefore, in pure resistive circuit, there is no phase difference between the voltage as well as current. In other words, both voltage and current are in same phase. AC circuit consisting of pure inductance. Consider an AC circuit which is containing only inductance. So the applied voltage V is represented as V is equal to V naught sine omega t. So if we plot a graph of V versus I, it shows that the voltage is leading or current is lagging behind the voltage by an angle of 90 degree. In other words, I is equal to I naught sine omega t minus pi by 2 because current is lagging behind the voltage by an angle of 90 degree. That's why minus pi by 2. Where I naught is equal to V naught divided by omega L. Omega L is nothing but inductive reactance that is represented as XL. Therefore, I naught is equal to V naught by XL. XL is inductive reactance. Here, the current lags behind the voltage by an angle of 90 degree. In complex form, it can be represented as inductive reactance XL is equal to J into omega L. Circuit consisting of capacitance. Consider the circuit which AC voltage is fed to a capacitor. Then the applied voltage will be given by V is equal to V naught sine omega t. So the graph of V versus I is represented like this. Here current is leading the voltage by an angle of 90 degree, but I is equal to I naught sine omega t plus pi by 2, where I naught is equal to V naught by 1 over omega c, where 1 over omega c is equal to xc. Therefore, I naught is equal to V naught by xc. Xc is called as capacitive reactance. Here the current leads the applied voltage by an angle of 90 degree. So in complex form, capacitive reactance can be represented as Xc is equal to minus J by omega C. It is also is equal to dividing and multiplying by J will get minus J square will be equal to plus 1 divided by J omega C. Next we'll move on to AC circuit containing inductance and resistance. Consider the circuit containing an inductor with inductance L and resistor with having the resistance R. So here the applied voltage will be equal to V. Consider an inductor of inductance L and resistor of resistance R connected in series with an AC source of voltage V is equal to V naught e power j omega t. Complex current at any instant of time is I. So we can, since it contains the resistance as well as inductance, we have already studied that it contains two parts, a real part of R and imaginary part of reactance of due to inductance, that is inductive reactance. The combined opposition, that is impedance, is acting along the z direction. Now applying Kirchhoff voltage law to the circuit, where VL is the voltage across the inductor and VR will be the voltage across the resistor. Then V is equal to VR plus VL, that is supplied voltage will be equal to the sum of voltage across the resistor and voltage across the inductor. So we know that VR is equal to I into R and VL is equal to I into XL. Here R is the resistance and XL is the inductive reactance. But we know that XL is equal to J omega L in complex form. Therefore, V is equal to I into R plus J omega L. So in terms of I, we can represent I is equal to V divided by R plus J omega L. So replace this R plus J omega L as impedance Z, where Z is equal to R plus J omega L. Z is a vector. Its value will be equal to modulus of Z e power j phi, where phi is the phase angle and it is positive. Therefore, that equation can be represented as I is equal to V is V naught e power j omega t. In exponential form, V can be written as V naught e power j omega t and Z can be written as modulus of Z into e power j phi. Further simplification of this expression, I will be equal to V naught. So e power j phi ನ ಮೇಲ್ ಕಳಿಸಿದ್ರೆ ಮೈನಸ್ ಆಯ್ತು e power j into omega t minus phi whole divided by modulus of z, where z is equal to square root of r square plus omega square l square. Therefore I is equal to v naught e power j omega t minus phi divided by square root of r square plus omega square l square. Replacing this whole constant term, that is V naught divided by square root of r square plus omega square l square as I naught. This expression can be written as I is equal to I naught e power j omega t minus phi. Call this as equation number 1. From equation 1, I naught is equal to V naught divided by square root of r square plus omega square l square is the peak value of current, and modulus of z is equal to square root of r square plus omega square l square is the impedance of the circuit, and phi is equal to tan inverse of XL divided by R, that is the phase angle between voltage and current. On the equation 1, that is I is equal to I naught e power j omega t minus phi, we can conclude the equation as amplitude of current I naught depends on the frequency, that is omega is equal to 2 pi f of applied voltage. Here the peak value of current, that is I naught, depending on the frequency. You can observe here it depends on the frequency of the applied voltage. Since it is AC, so we can change the frequencies. So maximum value of current is depending on the frequency of the voltage applied. And second thing we can conclude from equation 1 is the current lags behind the voltage by a phase angle of phi. Here voltage is leading and current is lagging. So current and voltage, there is a phase difference of phi. And that phi depends on the frequency applied. And the third one is that is called as complex impedance, containing real part which is equal to resistance and imaginary part which is equal to inductive reactance. These are the three conclusions we can came from equation 1. Here the value of inductive reactance is XL is equal to omega L. Omega is equal to 2 pi f into L. XL is equal to 2 pi fl in terms of frequency. The references for this session are listed. Thank you.